experimental determination of height of capillary rise of water in a capillary tube. Let us take water into a beaker and keep it on a stand. Keep it on a stand. Then hold the capillary tube. Hold the capillary tube with a clamp attached to a retort stand. Attached to a retort stand. A capillary tube is held vertically by a clamp which is fitted to a retort stand, and this capillary tube is dipped in water. A part of the capillary tube is dipped in water. Then a pin is attached to the capillary tube. A pin is attached to the capillary tube such that its tip just touches the surface of water. Then we notice the liquid column inside the capillary tube. We notice the raised liquid column inside the capillary tube. A microscope is focused to this liquid column. A microscope is focused onto this liquid column. First, the microscope is focused to the lower meniscus of the liquid column inside the capillary tube. By raising or lowering the microscope, we focus the microscope to the lower meniscus of this liquid column inside the capillary tube. The horizontal wire in the microscope, the horizontal cross wire in the microscope is made to coincide with this lower meniscus. Then the reading will be taken on the vertical scale of the microscope. A reading will be taken on the vertical scale of the microscope. It is indicated by R1. Then the beaker is raised slowly and the stand will be removed under the beaker, and the beaker is lowered so that the tip of the pin is visible clearly. Then the microscope is lowered. By lowering the microscope, it is focused to the tip of the pin. Which indicates the surface of water. Once again, the horizontal crosswire is made to coincide with the tip of the pin, and the reading is taken on the microscope. Vertical scale of the microscope. It is R2. The difference of these two readings, R1 and R2, gives the height of the liquid column, the height of water column inside the capillary tube. Now the capillary tube is turned horizontally and held with the clamp. The capillary tube is rotated to the horizontal position and held firmly with the clamp. The cross section of this capillary tube, the microscope is focused onto the cross section of this capillary tube. Then we notice a white circle. The vertical crosswire is coincided on one side first, and the reading will be taken. Then the microscope is moved to the other side, and another reading is taken. The difference of these two readings gives the diameter of the cross section. Similarly, the horizontal crosswire is coincided with the top surface of the circle, and a reading is taken. Then it is moved down and it is made to coincide with the bottom surface of the cross section, and another reading is taken. The difference of these two readings gives another diameter. Then the average of these two diameters gives the diameter of this cross section, capillary tube cross section, and then the radius is determined, which is half of the diameter. Like this we determine the radius of the capillary tube. We have determined the height of the liquid column H, the radius of the capillary tube R. Then the density of the liquid and acceleration due to gravity are assumed. Then we calculate the surface tension we calculate the surface tension with the relation T is equal to half R dz into H plus R by 3 into H plus R by 3. Using this relation, the surface tension will be determined. Variation of surface tension. Surface tension decreases with the temperature of the liquid. As the temperature of the liquid rises, the surface tension decreases. We can explain this decrease with the increase in kinetic energy of the molecules. As the temperature increases, the kinetic energy of the molecules increases, and thereby the energy required to come to the surface of the liquid, the surface of the liquid will also decreases. It decreases. The energy required to come to the surface decreases. Hence, the surface tension decreases. Hence, the surface tension decreases. Surface tension will also decrease with the impurities present inside the liquid. It also decreases with the impurities present in the liquid. Excess of pressure. The pressure inside a drop of liquid is more than the pressure outside. This difference in pressure is known as excess pressure. Pressure inside the liquid drop is more than the pressure outside. If P in represents the pressure inside the liquid drop, if P in represents the pressure inside the drop and P out represents the pressure outside the liquid, then P in minus P out is equal to P, which is the excess pressure, in the liquid drop. We know that pressure is force per unit area. So when pressure is present, forces are present, which are normal. Now, there are two forces acting on a liquid which keep the liquid in an equilibrium state. One is the force due to surface tension. The other one is force due to the excess pressure. These two forces are shown in the figure. The pressure inside the liquid pushes the liquid to expand. Hence, this applies a force. And the surface tension forces act inside the surface of the liquid. These forces try to shrink the liquid drop. Hence, the liquid drop will be in equilibrium state when these two forces are equal. That is, force due to surface tension and force due to excess pressure. When these two forces are equal, then only the liquid drop will be in equilibrium state. If we consider a hemispherical droplet, as shown in the figure, the force due to the excess pressure acts in the upward direction, and the force due to surface tension acts in the downward direction. The liquid drop is in equilibrium when FP, force due to excess pressure, is equal to FST. FP, force due to excess pressure, FST, force due to surface tension. When Fp is equal to Fst, the drop is in equilibrium state. Relation for excess pressure. Force due to surface tension is equal to length into surface tension. Force due to surface tension is equal to length into surface tension. So Fst is equal to 2 pi r into T. 2 pi r is circumference of this hemispherical cross section. 2 pi r into T. Then force due to excess pressure is equal to pressure into area. So Fp is equal to pi r square into P. P into pi r square. Since Fp is equal to Fst, P into pi r square is equal to 2 pi r into T. 2 pi r into T, from which we get P is equal to 2T by R. Relation for excess pressure in a soap bubble. Relation for excess pressure in a soap bubble. In a soap bubble, there are two surfaces. So, force due to surface tension is equal to 2 into 2 pi r into T. That is 4 pi r T. Force due to excess pressure remains the same, P into pi r square. Hence, P into pi r square is equal to 4 pi RT, from which we will get P is equal to 4T by R. This is the relation for excess pressure in a soap bubble.